the next algorithm we have for helping to find a minimum cost Hamiltonian circuit is the sorted edges algorithm. And remember, these algorithms are not going to definitely give us the minimum cost circuit. They are going to help us find one with a potentially smaller cost than others. As we saw in the nearest neighbor algorithm, with this graph, it gave us actually the most expensive circuit. But in the other graph, we used it and found some that had lower cost. So sorted edges algorithm. First, arrange the sides in order of increasing cost. So just make a list of all the sides in order of increasing cost. Select an edge of least cost such that 1. It never requires 3 edges meet at a vertex. 2. It never creates a circuit that does not include all vertices. You're done when you can no longer do this. Well, or you can also say you're done when you've created a Hamiltonian circuit. So let's apply the sorted edges algorithm to the 2 examples we've done. And this board is getting dirty, so let's erase a little. So apply the sorted edges algorithm to this first one. Well, first what we're going to do is list all of the edges in increasing cost. So 300 is the smallest, 349, 425, 541, 562, 774. And now what we're going to do is add edges to this until we can't, or unless, or until, until we can't. So what I'm going to do to add these edges is just draw this graph like that and add the edges as we can. So starting at 300. Well, if we add the edge that costs 300, does that violate one of these 2? Well, no. We'll see what happens when those 2 are violated as we go. And I know I didn't say anything about it yet, but I'm planning to. So we can add 300, so that's okay. How about 349? What happens if we add 349? That's this one. Well, that's okay. That doesn't have 3 edges meeting at a vertex, and that never creates a circuit that does not include all vertices. So we could add this one. We could add this one. What about 425? Well, what happens if you add this 425? What does it look like? You might not want to write this if you don't have an eraser. If you add 425, well, look what happens. You're visiting Chicago now 3 times. We know we need to start and end, potentially, at Chicago, but we can't visit it 3 times. So when we add, if we add 425, that would violate number 1 here. It has 3 edges meeting at a vertex. You're visiting a city 3 times. So select an edge of least cost such that 1, it never does that well. That means we can't add 425. So what I like to do when that happens is just cross it out like that. What's the next one? 541. 541. Which one is that? 541 is that. Well, that creates a circuit, but it's a circuit that doesn't hit all vertices. So it creates a circuit that does not include all vertices. So we cannot add that. It violates number 2 over there. So we can't add, what was that number? 541. Well, from there, can we add 562? What happens? Well, that's okay. That doesn't have 3 edges meeting at a vertex. And it does not create a cycle that doesn't include all vertices, so that's okay. And 774, the same thing. It does not have 3 edges meeting at a vertex. It does create a cycle, but the cycle includes all vertices. So the sorted edges algorithm, that does not say edges at all. Sorted edges algorithm gives which circuit? C, S, M, D, C, which is not the minimum cost one. This one has cost. Which one was this? This was the one that ended with 5. So 1985, which which is not the minimum cost. Yes, 1985. But the algorithm gave that one. The sorted edges algorithm could also give the one of most cost, depending on the graph. But in this case, it did not give the one of lowest cost. But with many, many vertices, it may be useful. Let's do the sorted edges algorithm on that other graph, that graph with 5 vertices. That's a long line. So we have A, B, C, D, E, line, 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 line. And we had costs on all of these, so we have 400, 700, 600, 500, 800, 950, 650, 750, 550, and 850. Is that all of them? There should be 10 numbers. Yes, 10. So apply the sorted edges algorithm here. And again, I like to do this by drawing the nodes and filling it in like I did over there. So example. Apply the sorted edges algorithm. So let's apply the sorted edges algorithm. What do we do? Well, we list out all of the edges in increasing cost. So let's do that. In increasing cost, the lowest is 400. Then what? 500. 550. 600. 650. 700. 750. 800. 850. There could be 2 with the same. If you had 2 with the same, you'd have to check both of them. That's why this says select an edge of least cost instead of the edge with least cost. So what is this? 1, 2, 3, 4, 9. So we're missing 1, 950. And what we're going to do is add these until we can't. 400. Where's 400? That's here. So that's okay. 500. Can we add 500 without screwing things up? Yes. Because 500 is over here. The only ways it can go wrong is if we have 3 meeting at a vertex, if you visit the same city 3 times, or if it creates a circuit that does not include all of the vertices. So we could add 500. What about 550? Where's 550? Yes, we can add that. How about 600? Can we add 600? Well, if we add 600, well, looks like we can. We can add 600. How about 650? Can we add 650? Which one is 650? That's A to C. Well, look what happens if you add from A to C. It creates the circuit ABC. Well, ABCA. So you can't add 650. What about 700? Where's 700? 700 is A to E. Can we add that? Well, again, that would create a circuit. If we added A to E, it would create the circuit ADEA. So we can't add 700. How about 750? Which one's 750? From E to C. Well, yes, we can add that. While it creates a circuit, it is a circuit which hits all of the vertices. So it's okay. And once you do that, you don't have to even consider the last few. So the sorted edges algorithm gives which circuit? I'm going to start at A, I guess. A, B, C, E, D, A. You can start at whichever one you want. With cost, this looks like the same one we had before with that 2800, is it? No, it's not. So 15, oh wait, it is. I labeled something 500 instead of 550. My bad. So 1500 plus 13, yeah. So with cost, 2800. So these algorithms, definitely practice these algorithms. They are good to get used to. They're nice for piecing together graphs. Now these finding minimum cost Hamiltonian circuits is actually a very famous math problem. It's called the traveling salesman problem. And a statement of the traveling salesman problem is find the trip of minimum cost that a salesman can make in order to visit the cities in a sales territory once and only once, starting and ending at the same city. So that's what we're actually doing here. In a slightly different context, we're trying to solve a famous math problem called the traveling salesman problem, which reduces to finding a minimum cost Hamiltonian circuit. I'll read it one more time. Traveling salesman problem, find the trip of minimum cost that a salesman can make in order to visit the cities in a sales territory once and only once. So, I'm not going to say solve the traveling salesman problem in this example. I'm going to probably phrase it more like something. Here are a bunch of cities and distances, or a bunch of cities and cost to travel between them. Find the minimum cost. Well, apply this algorithm to find a Hamiltonian circuit and what is the cost. But we talked about complete graphs, so I'm just going to formally define a complete graph. So I should do that, and it's something that you should know if you're taking a graph theory course, which for these 3 weeks we are. So definition: a graph is called complete if there is exactly one edge between each pair of vertices. So a graph is called complete if there's exactly one edge between each pair of vertices. And we've seen the complete graph on 4 vertices and on 5 vertices. Okay, I guess I could draw with 2 vertices. There's the complete graph on 2 vertices. The letter we use for a complete graph is a capital K. I believe it's because a German word for complete probably starts with K. I'm not positive. I should probably look that up. But here is K2, a complete graph on 2 vertices. A complete graph on 3 vertices would look like this. There's K3. K4, I'm going to draw up here. There are actually 2 different ways you could draw K4. One of them we've seen. So I'll say 2 representations of K4. So right here, there's a complete graph on 4 vertices. Notice on 2 vertices, there's exactly 1 edge going out of each vertex. On 3, there are exactly 2 edges going out of each vertex. On 4, there are exactly 3 edges coming off of each vertex. But there is another representation of that. Right there is another representation of the same graph. So here we have 2 different ways we could write K4. Sometimes the first one is preferred because it doesn't create an additional intersection. Sometimes this is preferred because, I don't know, I like how that one looks. Because it's, going from line to triangle to square. Here's a complete graph on 5 vertices with a pentagon. But why do these give the same graph? Well, a couple ways you could reach that conclusion. One of the ways is if you label all of the edges A, B, C, D, A, B, C, D, and list the edges like A, B is an edge, A, C is an edge, A, D is an edge. And in each case, you'll get the same 6 edges. That's one way to see it. Another way to see it is a little more abstract. And how could you see that? Well, take this graph. Pretend that this is, I don't know, like circular things that are held together by a string. An elastic string, let's say. And what would happen if you lifted this middle vertex and just put it all the way up here? What would happen to those elastic edges? Well, if you put it up here, it would turn into something almost like a square. These 2 edges would go out and make the border of our square, and this diagonal would go across this other one. And so if you take this and stretch it out over to here, you will get a graph just like that one. K5 is over there. We'll do just one representation. So K5 is here. What about K6? Let's just draw K6. So K6 will start with a hexagon, like that. And then we need to draw lots of extra edges. Yes, we need 5 coming out of each one. 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5, 5, and 5. So right here we have K6. So a complete graph just has exactly one edge between each vertex, and they all have nice visuals. I mean, you can draw them with the n-gon and then just connect edges like this. But K4 does have this other representation.